Hey, ninth grade. Okay, today's lesson, complex numbers and roots, page 350. Okay, so first, let's define imaginary number. An imaginary number is the square root of a negative number. Remember, square roots of negative numbers are not real. For example, square root of -4, there is no number that multiplied by itself that is going to be equal to -4. Okay, for example, 2 times 2 equals 4. -2 times -2 equals +4. So there's no such number that multiplied by itself that is equal to -4. Therefore, this is why imaginary numbers were invented. Okay, so imaginary number is the square root of a negative numbers. Now, imaginary numbers can be written in the form bi, where b is the real number and I is the imaginary unit. I is equal to square root of -1. Okay, keep this in mind. I is equal to the square root of -1. Now another example, square root of -2. We can rewrite square root of -2. We can rewrite this as a product of square root of -1 times square root of 2. Okay, -1 times 2, that's -2, square root of -2. And since I is equal to square root of -1, so we simplify. Instead of writing square root of -1, we write I times square root of 2. So square root of -2 is equal to I square root of 2. Now, square root of -4, we can rewrite this as square root of -1 times square root of 4. Square root of -1 is equal to I. Square root of 4, that's 2. I times 2, it's equals to 2I. So square root of -4 equals 2I. Okay? So that's what imaginary numbers are. Now, the square of an imaginary number is the original negative number. For example, I squared. Okay, by definition, we know that I is equal to square root of -1. So I squared is equal to square root of -1 squared. Now we simplify. Notice, we cancel the square root with the squared. So what do we get? The same negative number, -1. Okay? Very good. Now, example 1. If we look at example 1, it says, express each numbers in terms of I. So part A, we have 3 square root of -16. Okay? How are we going to express this in terms of I? So we have 3 square root of -16. Okay? So we can express a square root of -16 using -1, square root of -1 times square root of 16. Okay? Does 16 has a perfect square? Yes, that's 4. And we know that square root of -1 by definition is equal to I. So we can simplify. 3 times I times 4. 3 times 4, that's 12. Times I, 12I. Okay? Now, part B, we have negative square root of -75. So we can rewrite this as negative square root of -1 times square root of 75. Okay? Now, does square root of 75 has a perfect square root? No, we don't. So let's simplify by finding the prime factorization of 75. Prime factorization. 75 divisible by 2? No. Divisible by 3? Yes. 3 times 25. 25 divisible by 3? No. By 4? No. By 5? Yes. And 5 divisible by 5 equals 1. So this is our prime factorization. So we can rewrite this as negative square root of negative 1 times square root of 3 times 5 squared. Okay? Negative square root of negative 1 times square root of 3 times square root of 5 squared. Okay? Now we simplify. Square root of negative 1, that's I. Negative I times square root of 3. Square root of 5 squared, we simplified. Cancel the square with the square root, that's times 5. Okay? Now, negative times 5, negative 5i times square root of 3. So this is equal to negative 5i square root of 3, or we can write it as negative 5 square root of 3i. Okay? So we have two different ways of writing that solution. So if the square root does not have a perfect square, then you have to find the prime factorization. Okay? Always find the prime factorization. Now, here we have examples of how to solve a quadratic equation with imaginary solutions. So example 2 says, solve each equation. Part A, x squared equals negative 81. Okay? So we want to find the value of x, not x squared. So how do we leave x by itself? Since we have x squared, we're going to square root on both sides of the equations. So what happens? We can cancel the square with the square root, and we get x equals square root of negative 81. We can express square root of 81 as x equals square root of negative 1 times square root of 81. Okay? 81 has a perfect square? Yes. 9 times 9, 81. So this means square root of negative 1, by definition, equals I, times square root of 81, 9. I times 9 equals 9i. So this equation has imaginary solution. Now, part B, it says 3x squared equals negative plus 75, plus 75 equals 0. Okay? 3x squared plus 75 equals 0. So we want to leave x by itself. So we pass 75 to the other side of the equation. We get 3x squared equals negative 75. Now we leave x by itself. Divide by 3 on both sides of the equation. And we get that x equals negative 75 divided by 3, which is equal to negative 25. And that was x squared, x squared equals negative 25. Now let's find the value of x. How do we leave x by itself? By square root on both sides. We cancel square with square root, and we have that x equals square root of negative 25. Okay, now we can express this in the form x equals square root of negative 1 times square root of 25. X equals square root of negative 1. 5i times square root of 25, 5i times 5, 5i. Okay, and this is an equation with imaginary solutions. Now, a complex number is a number that can be written in the form a plus bi, where a and b are real numbers and I is equal to square root of -1. Every complex number has a real part a and an imaginary part b. So if we have a plus bi, a is the real part and b is the imaginary part. Okay? So, complex numbers. Now, complex numbers, okay, we're going to call this set C. Okay, complex number set C. Okay, it has two subsets, which are real numbers and imaginary numbers. Okay, don't forget that real numbers, we have rationals and irrationals. Okay. Okay, don't forget that rational numbers is a number written in the form a over b, where a and b are real numbers, right? So in the set of rational numbers, we have fractions and terminating and repeating decimals. Okay, we have fractions, terminating and repeating decimals. We have integers. We have whole numbers. And finally, natural numbers. Okay, so this is how we classify complex numbers. Now, notice, in the complex numbers, a plus bi, okay, if a and b, are not equal to 0, then we call them complex number. Right? If a equals 0, if a equals 0 and b is not equal to 0, okay, then if a equals 0, then we're talking of a pure imaginary number. If a is not equal to 0 and b equals 0, then we're talking of a real number. Okay? So if a and b are not equal to 0, complex number. If a equals 0 and b is not equal to 0, pure imaginary number. Okay? Examples of pure imaginary numbers: 4i, 2i, negative 7i, pure imaginary. If a equals 0, if a is not equal to 0, sorry, and b is equal to 0, then we're just talking of a complex, if a real number. Now, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Okay? So two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So look at example 3. So example 3, equating two complex numbers. It says, find the values of x, the value of x and y that make the equation 3x minus 5i equals 6 minus 10y I true. Okay, so we have the equation 3x minus 5i equals 6 minus 10y I. Okay, so if you notice, we have two complex numbers and we're saying that they are equal. Okay, two complex numbers and we're saying that they're equal. Now, again, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So let's define first the real parts. This and this are the real parts, of 3x is the real part of this complex number, and 6 is the real part of this complex number. And this negative 5i will be the imaginary part, and negative 10yi will be the imaginary part of the other complex number. Okay, so again, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So let's put the real parts together. Look, 3x is equal to 6. This is the real part. 3x equals 6. And the imaginary part will be negative 5i equals negative 10y I. Okay? So, what will be the value of x? Let's solve for x. 3x equals 6. Divide by 3. X equals 6 divided by 3. X equals 2. Now, in the imaginary part, we can cancel the y's in common, and we get negative 5 equals negative 10y. So let's find the value of y. Let's leave y by itself, so we're going to divide by negative 10. So we get negative 5 over negative 10 equals y. Negative divided by negative, that's positive. 5 over 10 equals y. 5 and 10 are divisible by 5, so we can simplify. 5 divided by 5, that's 1. 10 divided by 5, that's 2. So y equals 1/2. Okay, So the value of x equals 2 and the value of y equals 1/2. Okay, now let's do the check. Check. We have 3x minus 5i equals 6 minus 10yi. Okay, so the value of x is 2. Let's simplify this. 3 times 2 minus 5i equals 6 minus 10 times y times 1/2 I. 3 times 2, 6 minus 5i equals 6 minus half of 10, 5i. So here we go. The complex number 6 minus 5i is equal to 6 minus 5i. True. Okay? So this is how to find the values of x and y that make the equation true. You've put the real parts together as an equation and then the imaginary parts together as an equation. And that's how to solve example 3. Finding complex zeros of quadratic function. Finding complex zeros of quadratic functions. Okay, so example 4 says, find the zeros of each function. Part A, f of x equals x squared minus 2x plus 5. So we have to find the zeros of the function, okay? So how do we do this? Okay, x squared minus 2x plus 5 equals 0. Okay, so here we have our quadratic function. Now we wrote it as a quadratic equation that it's equal to 0. And we're going to solve this by completing the square. Okay? Remember how to complete the square. First step, plus 5, we pass it to the other side of the equation. And we get x squared minus 2x equals 0. If we had plus 5 on this side, on the other side, that's negative 5. 0 minus 5, negative 5. Okay? Now, we're going to complete this squared. Okay? How do we complete the squared? We find half of b. b in this case is equal to negative 2. So we have to find half of b squared. Okay? And in this case, b equals negative 2. So that means negative 2 over 2 squared equals negative 2 divided by 2, that's negative 1 squared equals 1. Okay, so we complete the square. X squared minus 2x plus 1 equals negative 5 plus 1. Okay. Now, since this is a perfect square binomial, we find the binomial squared, which is going to be equal to x minus 1 squared equals negative 5 plus 1, negative 4. Now we use the square root property, square root on both sides. Square root on both sides, sorry. So we simplify and we get x minus 1 equals positive negative square root of negative 4. We can rewrite square root of negative 4 as x minus 1 equals positive negative square root of negative 1 times square root of 4. Right? X minus 1 equals positive negative square root of negative 1, that's I, times square root of 4, that's 2. I times 2, x minus 1 equals positive negative 2i. Okay? Now we leave x by itself. And we get that x equal So aquí es negative 1. On the other side, 1, positive 1 plus minus 2i. And there we have our two complex numbers. Remember this, 1 plus minus 2i, this is equal to 1 plus 2i and 1 minus 2i. Okay? And here we have our two complex numbers. Now, part B, we have g of x equals x squared plus 10x plus 35. Again, we write it as a quadratic function equation, x squared plus 10x plus 35 equals 0. Pass 35 to the other side and we get x squared plus 10x equals negative 35. Now we're going to solve by completing the square. How? Half of b squared. In this case, b is equal to positive 10. So that means half of 10 squared. Half of 10, that's 5 squared, equals 25. Okay? So x squared plus 10x plus 25 equals negative 35 plus 25. Okay? Now this is a perfect square trinomial, so the binomial squared will be x, como este es positive 5, plus 5 squared equals negative 35 plus 25, that's negative 10. Okay, now we use the square root property, square root of both sides. X plus 5 equals positive negative square root of negative 10. Okay, so we can rewrite square root of negative 10 as positive negative square root of negative 1 times square root of 10. X plus 5 equals positive negative square root of negative 1, that's I, times square root of 10. It doesn't have a perfect square, so we get square root of 10. I times square root of 10, that's equal to positive negative square root of 10 I. Now we leave x by itself, we pass plus 5 to the other side, and we get that x equals, if we had positive 5 here, on the other side it will be negative 5 plus minus square root of 10 I. Okay? Now, como square root of 10 doesn't have a perfect square, if we find the prime factorization, 10 is divisible by 2, which is equal to 5, and 5 is divisible by 5 equals 1. So we cannot simplify it, so that's why we leave it as square root of 10. Okay, and this is how to find complex zeros in quadratic functions. Okay, the solutions: negative 5 plus I square root of 10 and negative 5 minus I square root of 10 in example 4b are related. These solutions are complex conjugate pair. Their real parts are equal and their imaginary parts are opposites. The complex conjugate of any complex number a plus bi is the complex number a minus bi. That is, if we have a complex number a plus bi, okay, then the complex conjugate is going to be a minus bi. Notice that a and b, they don't change. What changes is that the addition sign will be negative. If this is negative, it will be then positive. So if we look at example 5, it says find each conjugate. Finding complex conjugates. Example 5. Find each complex conjugate. Now, part A, it says 2i minus 15. Okay? So remember that a complex number is written in the form a plus bi. Notice that in example 5a, we have 2i minus 15. So if we want to write this in the form a plus bi, then in this case, a, the real part, is negative 15, and the imaginary part is 2i, positive 2i. Now we have our complex number. So the conjugate, notice, the conjugate will be the same real part, negative 15. Now the imaginary part will be the opposite. What is the opposite of positive 2i? Negative 2i. And that will be the complex conjugate of 2i minus 15. Now in part B, we have negative 4i. This is an example of a pure imaginary number. Now, if we want to write this in a complex form, a plus bi, negative 4i is equal to 0 plus negative 4i, or 0 minus 4i. Yes, that will be the complex number. So the complex conjugate, the real part remains the same, 0, and the imaginary part are the opposite. So the opposite of negative 4i, it will be positive 4i. And that will be the complex conjugate of negative 4i. So that's it, guys, for your homework. Homework number 4. Page 353, problems 2 through 34 even. Okay, page 353, problems 2 through 34 even. Sorry, actually, and 38 through 56 even. Okay, that's it, guys. See you next week.